All right, so in this section we're going to look at anti-differentiation by parts, or integrating by parts. Those are both the same things, and it allows us to undo the product rule, basically is what it allows us to do. So some functions will integrate by parts, others won't. Some integrate by parts, but it takes several steps. So this is just kind of one of those things that can be really challenging. However, if you do it right, you'll get an answer and you'll know that you've got it right. A couple things. Here's what your formula looks like. It's in this red box here, and this is how we're going to break it up. We're going to break our function up into two things. So I'm going to have a u and then a dv. So when I look down here, like in the inaction part, one of these is going to be a u and one of these is going to be a dv, and I'm not sure which yet, but we're going to separate it out into different parts. And to choose a u, follow kind of this blue box over here on the right. So always look for a natural log first, then an inverse trig function, then a polynomial, then an exponential, then a regular trig function. The whole thing is we want u to be something that simplifies when it's differentiated, and we want the dv part to be something that remains manageable when integrated. Okay, so that's a lot to swallow right now, but let's see how it looks in action. Work this out with me as you're working it at home, and we'll check it out. So x cosine x, the integral of x cosine x dx, and we want to use the formula in the red box. And so what we're going to do is we want to pick something that is easy to take the derivative of. And honestly, the easiest thing is the x. So we're going to let u equal x. That means then that the dv, the v du part, or the dv part, is going to be cosine x dx. Okay, we want u to be something that simplifies when differentiated. Hey, there's nothing easier to simplify than x. The derivative of x is 1. It's no problem. We want something that remains manageable when integrated. Hey, integrating cosine x dx, that's manageable. Okay, that's not going to give us a horrible thing to deal with. So back to our problem here. Now go ahead and take the derivative. So du is equal to 1 dx. Go ahead and integrate so that v is equal to sine x. Okay, so I took the derivative of u, I integrated dv, and then I plug all those back into my new formula. So I'm going to take u times v, x sine x, minus the integral of v du, minus the integral of v times du. And all of a sudden, that nasty integral we were looking at a second ago is a lot easier on the eyes, because I know how to take the integral of sine x. And the integral of sine x is negative cosine x. So I've got x sine x plus cosine x plus c. And if you can't remember your integral parts, just look on your trig card or find a resource where you've got a list of all your integrals, but sine x pops out really nice. And so this really complicated problem that we can't do a regular u substitution on winds up being not so bad. Sometimes we're going to have to use parts more than once, and you just have to hang in there and don't give up. And so the question on the left, we're going to use parts more than once. The question on the right, we're going to actually do it's kind of looping. It's called an unknown integral, and it's really interesting. So we'll start over here on the left, and what I'm going to do is I'm looking for something that I can take the derivative of really nicely. And so when I'm looking at this guy, I'm thinking I'm going to let u equal x squared. because the derivative of that is good. And if I have to take the derivative more than once, the derivative of x squared will eventually become a 1 or a 2 or just some constant. So I like that. I'm going to go for dv. I'm going to let that be the e to the x part. And the reason I picked that is because when I integrate e to the x, it stays e to the x. It's very easy to integrate. And no matter how many times I integrate e to the x, it's just going to be e to the x. So follow your formula, which is going to be, I'll just put it back up here on the corner of the page real quick. So we've got it. We're looking at the integral of u dv minus uv times the integral, u dv is equal to uv minus the integral of v du. Okay, so there's your formula. Well, when we set this guy up, then we're going to look at du, which is equal to 2x dx, and v, which is equal to e to the x. And so when I apply my formula, I've got uv, so e to the x, or let's go x squared e to the x, minus the integral of v du, let's write 2x first again, okay. So there's that guy. Now he's not done because I still really can't integrate the 2x e to the x part. So what I'm going to do is I'm going to keep my same u and same dv. So when I do it again, I'm going to go ahead, I'm still going to let u equal x. And I'm still going to let dv equal e to the x dx. Because what I want is du equaling 1 and v equaling e to the x. And we like this. Because then when I apply my formula again, I still have my first part from in purple. I still have that guy, x squared e to the x minus, but now I've got green, and so I do uv, which is x e to the x, minus the integral of v du, which is e to the x dx. And don't forget we've got this 2 right here. That 2 right there can pop all the way out into the front of the integral. So that 2, this purple 2, should still be, I forgot to write him down, that purple 2 should be right there. Because this guy right here in green is this integral right here. Okay, remember a constant can come out. Well, that's easy enough to integrate because when you integrate e to the x, it stays e to the x. So my final answer then, is going to be x squared e to the x minus 2x e to the x plus 2e to the x plus c. And that's all there is to it. So that guy, it takes a few steps, you have to repeat, but here's the trick. Right here where I let u equal x squared, let that u be the derivative of that guy. And right here where I let dv equal e to the x dx, let dv stay that same guy. Otherwise, you'll end up back where you started. Okay, on this other question then what we have to do is it's going to loop around. It's going to be what's called an unknown integral. And it's really kind of interesting how this works. So if you think the derivative of e to the x the whole time through is going to be e to the x. The integral of e to the x the whole time through is going to be e to the x. And then if you think about cosine, when you take the derivative of cosine, it's negative sine. When you integrate cosine, it's positive sine. And then sine and cosine continue to just flip-flop back and forth, and one will be negative and then positive and so forth. So what we're going to do on this guy is, let me separate these problems out real quick so we can get a clear difference. Okay, so what we're going to do on this, on the this looping one, is let's let u equal e to the x. Okay, it's easy to keep up with when you take a derivative. Cosine is too, but let's start here and see what happens. Okay, and then let's let dv equal cosine x. Okay, and so when I look at du, I get e to the x cos dx, and v, when I integrate that cosine, the cosine x just becomes sine x. So I use my formula. I get uv, so e to the x sine x, minus the integral of v du, so e to the x sine x dx. And then I do the same thing. And again, let u equal e to the x. So now I'm going to integrate this part right here. Okay, and so I'm going to let u equal e to the x again, and I'm going to let dv equal sine x. Okay, dx. There should be a dx on this guy too. Alright, so du is equal e to the x dx. V is now going to be negative cosine x. Okay. So follow your rule and keep that same guy in front. So e to the x sine x minus uv e to the x negative e to the x cosine x minus and then the integral of v du, which is negative e to the x cosine x dx. Okay, and if you'll notice, when I clean this guy up, and I'll write it in a different ink for the cleaned up version, I have e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. Now, check this out. This guy right here is where we started. Okay? So remember, we have an equality statement. We're saying that this guy right here is equal to the blue equation down here on the bottom. So what I'm going to do is add the integral of e to the x cosine x dx to both sides of that equation. So I'm getting low on space here. So what happens is I get 2, because it's just, I'm adding one of each, 2 e to the x cosine x dx equals e to the x sine x plus e to the x cosine x. And then how do you get this e to the x cosine x dx all by itself? You divide by 2. And then this guy right here will be our solution. Okay? And then lastly, Don't forget that plus c, which I'm out of room on. And when you get that plus c in there, you've got your solution and you're good to go. You can't really simplify it any more than this. And that's good. So it takes a few steps. It can be a little confusing, but after you've worked one out a couple times, you'll start to get the hang of it and see the pattern. Okay, let's tackle an initial value problem that's going to require us to differentiate by parts, or I'm sorry, integrate by parts. So let's just get our formula back up here real quick. Okay, so here's our formula. And we want to solve the differential equation dy dx equals x ln x, subject to the initial condition that y equals -1 when x equals 1. So basically what we want to do is solve this guy out. So let's let u equal the natural log of x. The derivative of that is going to be easy to deal with, and let's let dv equal x dx. And again, that'll be easy to deal with. Let's watch this, because usually what we would want to do is try and let u go first, or let u equal x, because x eventually goes away. And we would then allow for dv to be the natural log of x dx. But watch what happens in this problem. This is a little bit different. So when we integrate this guy, here's what we end up with. We end up with u times v. Here, let's see. The derivative of natural log x is 1 over x dx. And when I integrate this guy, I get x squared over 2. So I get uv, which is going to be x squared over 2 ln x, minus the integral of x squared over 2x dx. And this actually turns out to be not so bad. The reason is x squared and x cancel out. And so basically what I'm dealing with is x over 2. That's basically what I'm integrating. And if you think about that just a little bit, what you're really integrating then is 1/2 the integral of x dx, which is 1/2 times x squared over 2. So usually, so now we're seeing some different things develop here with how to pick u's and dv's, and it can be very tricky to choose it the way that will work most efficiently. But just hang in there. And so here I've got my solution. Okay. And we could clean it up a little bit if we wanted to. Shouldn't be, it's not too hard to do. We're just going to have x squared over 2 natural log x minus x squared over 4 plus c. And they're giving us in that initial condition when x is -1 and when y is -1. And so, or when y is -1, x is 1. So then we can just substitute everything back in for x's and y's and solve this guy out. And so what you're going to end up with is, remember this is a y equals equation, so what you're going to end up with is y -1 equals 1 squared over 2 natural log of 1 minus 1 squared over 4 plus c. Well, natural log of 1 is 0, so this whole thing goes away. And I've got -1 equals 1 over 4 plus c. And when I add the 1/4 to both sides, I get -3/4 for my c. So what is my equation on this guy going to end up being? Well, my final solution, final equation is x squared over 2 natural log x minus x squared over 4 minus 3/4, and all of that is what y is equal to. So there's your initial value problem. Hang in there. Working these things can be tricky. If you just work this problem again on your own without watching the video and see if you can get the same answer. Alright, tabular integration is a way that we can break integration by parts up into a kind of a different look. And it might, for some problems, in some instances, it might help it go a little bit quicker and easier. But there are a couple things that we have to follow along with. First off, we have to pick an f and a g. And what we want to do is we want to pick an f of x that takes a derivative very nicely. And then we want to pick a g that integrates really nicely. So on this particular problem, I'm going to let f of x equal x squared, and I'm going to let g of x equal e to the x. Okay. Again, x squared goes all the way down to 0 eventually, and e to the x integrates to e to the x every single time. So what I'm going to do is I'm just going to start here with x squared, and I'm going to start here with e to the x. And then I'm going to just take derivative of x squared until I get to 0. And then I'm going to integrate e to the x to get a column that matches. Okay. And so what we're going to do now is we're going to multiply across on a diagonal. So I'm going to do x squared times e to the x, 2x times e to the x, 2 times e to the x. Okay. And when I do that, I'm going to make sure that this guy gets multiplied by a positive number. I want to make sure that this guy gets multiplied by a negative number, and that this guy gets multiplied by a positive number. So what I end up with is, for my final answer, I end up with x squared e to the x times a positive 1. Okay. Plus 2x times e to the x times a negative 1. Okay. Times 2e to the x times a positive 1. And that is what my integral equals. So tabular integration can be really, really nice. Another example of tabular integration, and again, you want to pick f of x to be something that takes derivative really nicely and gets down to 0. So we're going to go with x cubed. That would leave sine x as our g of x. And so f of x here is x cubed, g of x is sine x. So pay attention on sine x, because when you integrate it, you're going to have some negative signs that run around. So go ahead and take the derivative of x cubed, and then integrate sine x. So when you integrate sine x, you get negative cosine x. When you integrate negative cosine x, negative sine x. When you integrate negative sine x, back to cosine x. And when you integrate cosine x, back to sine x. And now we're back to where we started. So if you have to do something with your trig functions, the sine and cosine, they should eventually start to repeat, and there's going to be a pattern there. Okay, so connect them with a diagonal line. And then add your pluses and minuses. And the pluses and minuses alternate, so that my final answer is going to be negative x cubed, cosine x, plus 3x squared sine x, plus 6x sine x, minus 6x cosine x. Minus 6 sine x. And then never forget, at the end, every time you integrate an indefinite integral, the plus c. Okay, a couple more problems. Anti-differentiating the natural log. This is just kind of interesting, and so I thought I'd work it out for you. And we can do this by parts. So let's let u equal ln x. That's the only choice we have. And let's let dv equal dx. This is the only natural way to break it down, because I only have two things. I've got a natural log x and I have a 1 dx. So that's the only way it can go. So du is equal to 1 over x dx, and v is equal to x. So when I do my by parts now, I'm going to have x natural log x minus the integral of x over x dx. And this whole guy right here is just 1. X divided by x is just 1. So I end up with x natural log x plus x plus c. Minus x plus c. Whoops. So just kind of interesting, and that's the rule. That's how it breaks out. The last guy is finding an antiderivative of the arc sine, and we want to find the specific solution to this, where we go through the point 0, 0. Anytime you're given a point, and sometimes it's hard to remember, but anytime you're given a point, you're given a value for x. So in this case, my x is equal to 0. And you're given a value for y. In this case, my y is equal to 0. And we get so bogged down in the math sometimes, we totally forget that we're given a value for x and a value for y. Okay, so we want to look at the integral of arc sine of x dx. And again, this is just like our natural log one. We only have one way we can really split it up. This guy right here has to be u. This guy right here has to be dv. So u is equal to arc sine x, and dv is equal to dx. Alright, so when you take the derivative of the arc sine, then you're going to end up with, and you might need to look at your trig card, but 1 over the square root of 1 minus x squared dx. And when you integrate dx, you just get x. Okay, so there's your two pieces on that. And so when you multiply, I'm going to have x arc sine x minus the integral of x over square root of 1 minus x squared dx. Now we're going to have to look for a u substitution. And the reason we want to look for u substitution is because I can't integrate this guy exactly how it's given to me. And so for my u sub on that, I'm going to look for, I'm going to let u equal 1 minus x squared. And so du is equal to negative 2x dx. See if I can get enough room for that in there. Okay. And so now this problem in orange, and by the way, go ahead and solve all the way out for dx. Like, what does dx have to be? It's got to be negative 1/2 du is what dx is going to be, x dx. And look, here's x dx right there. Okay, so what I'm going to end up with is x arc sine x minus the integral of negative 1/2, and I'll change back to green, negative 1/2, the integral of u to the negative 1/2 du. Okay, and when you integrate u to the negative 1/2 du, you're going to add 1 and divide by that new exponent. Okay, and so when I do that, Let's make this a little smaller here. When I do that, what I'm going to end up with, if you just integrate, and I'll come over here to the side a little bit, if you just integrate negative 1/2 the integral u to the negative 1/2 du, this is going to be negative 1/2 times u to the 1/2 over 1/2. And remember, these two guys right here are going to cancel out. Because if I do 1/2 divided by 1/2, then it cancels out and just becomes a 1. So I'm only going to be left with u to the 1/2 power. So back over here to my problem, I've got x arc sine of x, and remember the 1/2 cancels out, so plus u to the 1/2, okay, plus c. And what was my u? It's this 1 minus x squared part. And this is what y would equal. Alright, so now when I apply my initial condition of 0 for x and 0 for y, then what I'm going to end up with is going to be 0 equals x, whoops, which is going to be 0 times arc sine of 0 plus 1 minus 0 plus c. And all those guys go away. And the only thing that's going to be left here is a negative 1 right there. The only thing that's going to be left is going to be a negative 1. So my specific solution on this guy then is going to be y equals x arc sine of x plus 1 minus x squared minus 1. And this should be square rooted. Because it's to the 1/2 power. There you go.